Hello and welcome. I'm Dr. Sujata Suvarnapatki from the Department of Statistics of Ram Narayan Ruya Autonomous College, Mumbai. In this video, I'm going to explain to you the statistical inference using bootstrapping. These are the contents that I'm going to cover in this video: introduction, applications, comparison with parametric inference, methodology, resampling, bootstrap confidence intervals, and the merits and the limitations of bootstrapping. Bootstrapping or resampling method was introduced by Efron in 1979. The bootstrap comes from the phrase to pull oneself up by one's bootstraps, generally interpreted as succeeding despite the limited resources. It can be applied regardless of the knowledge of the distribution of the data. Bootstrapping is applicable in both the parametric and non-parametric scenarios. The objective is to estimate the sampling distribution from the sample available only, without the prior knowledge of the population distribution. A sufficient number of resamples, that is at least 1,000 for the confidence intervals, are taken from a sample selected which are of the same size as that of the original sample, and the scheme of sampling that we use is simple random sampling with replacement. The statistic under consideration is then computed for each resample and the parent sample as well. These estimates altogether depict the sampling distribution. Many conventional statistical methods of analysis make assumptions about the normality, including the correlation, regression, t-test, and the analysis of variance. When these assumptions of normality are violated, such methods may fail. Bootstrapping method is used when the assumptions of the parametric test are not satisfied and or the parameter of the interest does not have the standard sampling distribution. For example, median or difference between two medians. Bootstrapping, a database simulation method, is steadily becoming more popular as a statistical methodology. It is intended to simplify the calculation of statistical inferences, sometimes in situations where no analytical answer can be obtained. As computer processors become faster and more powerful, the time and effort required for bootstrapping decreases to levels where it becomes a viable alternative to the standard parametric techniques. Scenarios to apply the method of bootstrapping. Bootstrapping can be applied in the following scenarios. When we have small sample sizes with unknown population distribution, the assumption of normality is invalid or the data are skewed. The statistic under consideration is a nonlinear combination of the variables. For example, it could be a ratio of two variables. Or a location statistic other than mean is to be studied, for which the sampling distribution may be unknown. Let's take a look at comparison between inference using bootstrapping and inference using parametric method. The objective of the parametric inference and the statistical inference using bootstrapping is to obtain the sampling distribution of the estimate under consideration using the limited resources and to infer about the population. The traditional inference puts some restrictions on the assumptions and the shape of the distribution, while bootstrapping method assumes that the random parent sample is a good representative of the population. Bootstrapping method works efficiently for both parametric and non-parametric case. Bootstrapping gives estimates which are similar to that of the parametric methods. Let's try to understand a step-by-step procedure for the method of bootstrapping. Consider a sample of size n with unknown distribution. Let capital T be the statistic of interest. These are the steps that are involved in the method of bootstrapping. Step 1. Calculate T for the original sample. Step 2. Assigning equal empirical probability 1 by n to each sample element, start resampling. Step number 3. Compute T for the first resample selected and denote it as Stephen star. Step 4. Repeat steps 2 and 3 till we get sufficient number of resamples. Use these estimates T stars of T to estimate the desired statistic. The distribution of these T stars is considered to be an estimate of the population parameters distribution. In most of the cases, the distribution of the bootstrap estimate comes out to be approximately normal. The statistics obtained are interpreted in the usual manner. Here is an example of resampling. Resampling is nothing but drawing subsamples from a sample selected from a population. The size of every resample or bootstrap sample is n, which is same as that of the original sample. The number of resamples drawn is in general large. It depends on the type of the test or the statistics used. For finding the confidence intervals, at least 1000 resamples are expected to be taken. Greater the number of resamples, greater is the accuracy. For a given data, say for example, if we have x1, x2, x3, x4 and x5 as a original sample, which is fairly small in size, the bootstrap sample sets could be x1 star, x2 star, xn star, which will contain 5 units each, which are taken from the original sample x1, x2, x3, x4, x5, but the scheme of sampling is simple random sampling with replacement. Here are some methods of bootstrap confidence intervals. It is not enough just to get a point estimate of the estimator, but it is also important to find out the range within which you expect the estimate to lie. And that can be done using confidence intervals. Some methods of bootstrap confidence intervals are listed over here, and the simplest being a percentile method. The second method is bias corrected and accelerated method. We also have double bootstrap confidence intervals and T-interval. In percentile method of confidence interval, it is customary to take 2.5th and 97.5th percentiles of the ordered resample estimates of a statistic to calculate the bounds for the 95% confidence interval of the statistic, and also calculating them using standard error approach. With this example, I will be explaining you how to generate resamples and how to find out the point estimate and the 95% confidence interval for the statistic under consideration. So here is the original sample with 11 observations, median for which is 28. If the statistic under consideration is median, then we do not know the sampling distribution of the sample median. But in order to find out the estimate for the population median, we use the method of bootstrap. So here, sampling distribution of the sample median is generated, assuming B is equal to 1000, meaning the total number of resamples that you are going to take is 1000, and then 25th value and 975th value will provide 95% confidence interval for the median. It's very important for us to make use of a statistical software in order to generate the resamples, because generating large number of resamples manually is not possible. Let's see how to use method of bootstrap using the statistical tool R. The first and foremost thing that one does is to import the data file which contains the original sample, and it is stored in the form of a CSV file. This data file will be imported in R using the command read.csv file.choose. In order to use the method of bootstrapping, we need to install a package called as boot. After installing the package boot, we call for the library function boot so that we are able to generate the resamples and get the sampling distribution of the sample median as well as the corresponding 95% confidence interval using the method of percentile. We create the function to find out the median, and the function boot calls this function 1000 times. The function boot sends the data and random number vector to function f 1000 times. Each time the random number vector is different. So we then use the function boot, which is applied to the boot data, which is the imported CSV file. For that particular data, statistic f is computed, and this particular procedure is done 1000 times. Having generated 1000 resamples from the original samples, one can also find out the corresponding 95% confidence interval using the function boot.ci, and type is equal to percentile. So boot.ci, which is used on the boot object, which contains 1000 resamples generated from the original sample, and using the percentile method, we can get 95% confidence interval for the population median using the method of percentile or using the percentile method. In case if you want to change the confidence interval level, so instead of 95%, if you want to get 90% confidence interval, you can simply add an argument in the earlier function boot.ci, which is called as conf is equal to 0.90. If you use conf is equal to 0.90 as an additional argument in boot.ci, you'll be able to get 90% confidence interval for the population median using method of percentile. So this is how, using R, we can find out the sampling distribution of the sample median as well as the corresponding confidence interval for the median. Let's take a look at the merits and limitations of bootstrapping. Bootstrapping is simple to carry out with the aid of the computers. The bias in the confidence interval goes on decreasing with increase in the number of resamples generated. It is considered to be safe by some of the clinical trials guidelines when there are too few observations. So in clinical trials, this is a classic area wherein you can think of using the method of bootstrap, because generally the number of sample observations that you may have may be very few. Method of bootstrapping is gaining popularity due to the simple structure and the reliable estimates. Bootstrapping can be considered to be a complementary method to parametric methods, but not as a replacement. Anytime parametric methods happen to be more powerful methods as compared to the non-parametric methods, it is difficult to carry out bootstrapping without the aid of computers, and it may be inappropriate in case of a sample which is not a representative of the population. So here were a few of the merits and limitations of bootstrapping, and with this I have come to the end of the discussion on statistical inference using bootstrapping. Thank you very much.